you. Yeah. So this is based on two joint works with Nick Genis, Craig Gentry, Bayu Lee, and Daniela Michancio. I'll spend most of the time talking about the one that I think most of you didn't hear about yet. And then maybe I'll get to the other one. I probably will, at least a little bit. The focus is trying to get sort of practical, or at least in some instances, practical applications of homomorphic encryption of the fully variety. And if you look at the contemporary lattice-based homomorphic crypto systems, the good thing about them is that the thing you actually end up doing are very, very simple. I mean, if you need to use these homomorphic encryption schemes, the only thing you do essentially is sample numbers from some simple distributions and multiply matrices. That's all. On the other hand, the size of the ciphertext in those systems is typically big, at least a few kilobytes, and if you're trying to compute deep circuits, could be megabytes per ciphertext, which means that these matrices are big. So all you do is multiply them, but you multiply matrices of high dimensions, so it's still slow. So if you want to get something that's practically efficient, the key is to get your ciphertext to be smaller. And in this talk, my focus will be the rate. I mean, the size of the information that you manipulate versus the size of the encryption of that information. I'm going to go through a few slides, the basic background of LWE-based encryption. There will be some algebra. I'll try to be gentle. It's not much. That's almost summarize it. The starting point is, well, if you want to try to solve linear functions with a little bit of noise, it's hard. So that's basically the thing underlying Regev's definition of the learning with errors problem. You take a linear set of equations like S times A equals B, and you add a little bit of noise to it. So you have a secret matrix S, a public random matrix A, mod Q, and a noise matrix E, where the size of the entries in E is a lot smaller than your modulus Q. And now you're given A and B, and you need to find S, and that's hard. Or you need to find E. It's the same thing. It's even hard to distinguish B from just a uniform matrix modulo Q. So that's learning with error. Another useful variant of it that was proven to be equivalent by Applebaum et al. Is where the secret is not uniform, but rather is chosen from the same distribution as the error. So that's another useful thing that we use a lot. And the way we use it in almost all LWE-based security is this. Well, I renamed S to S prime because I'm going to use S for something else. So now I have S prime times A plus E equals B. So I'm going to move B, put it under A. I'm going to concatenate the identity to S prime, and I'm going to call that one S. And then I'm getting S times this concatenation of A and B, which I'm now going to call P, is E. Well, A was random to begin with. B, you cannot distinguish it from random, so the entire matrix P is pseudorandom. On the other hand, if you multiply it by your S matrix, which is now S prime concatenated with the identity, then you get something very small. So that's basically all we need for almost all of LWE-based encryption schemes. You have a pseudorandom matrix such that if you multiply it by the secret key, you get something very small. And with that, I can tell you what Regev type crypto systems is. Typically, when you describe Regev encryption, you describe it as encrypting a scalar, but really it encrypts the matrices. A scalar is just a one-by-one example. So you have a matrix M. This is your plain text. You want to encrypt it. You have a secret key that has this form of S prime concatenated with the identity. And your ciphertext, well, you just generate one of these pseudorandom matrices. and you add to it some representation of your plaintext. In this case, is a matrix that has 0 at the top and some encoding of the matrix at the bottom. And the point is, if you do the matrix multiplication, well, multiplying the secret key by the pseudorandom matrix gives you a little bit of error. Multiplying the secret key by this 0 encoding, just, the secret key gets zeroed out, and you only multiply the encoding by the identity. So what you get, the invariant of Regev encryption, is you take your ciphertext, you multiply it by the secret key, you get an encoding of M plus a little bit of error, and, well, you set your encoding in such a way that you can correct errors. So then you can recover your plaintext. So that's Regev encryption. There are many variants of it depending on how you encode and what the dimensions are, but they all look basically that. The second concept that I want to talk about in terms of background is redundancy that we need to add and gadget matrices. Gadget matrices, for the purpose of this presentation at least, is a way to represent some matrix that we care about, call it X, by some other matrix Y that has small entries and higher dimension, such that recovering the original X from your Y is a linear operation. And the simplest example of that is bit decomposition. So if X was your matrix, then you break it into Y0, it's the matrix of all least significant bit, Y1 is the matrix of the second bits, etc. So then X is just Y0 plus 2Y1 plus 4Y2, etc. So that's a linear way to reconstruct X from Y. And the matrix that represent that reconstruction we call G. It's a gadget matrix. It has other properties that I don't care about here. So X is G times Y. For the bit decomposition, this matrix G is just the identity, twice the identity, 4 times the identity, etc. We also denote by G inverse the operation of taking X and turning it into Y. G inverse is not a matrix inverse. G is not invertible. It doesn't have an inverse, but we use G inverse to denote this operation. One more thing about redundancy. So G inverse of X is a redundant version of X with low norm. And the more rectangular, the more short and wide G that we use, the smaller we can make the entries in G inverse of X. So the bit decomposition example that I showed before has log Q times the columns as the number of rows. So it's very, very, very wide. And you can make the entries being 0 and 1. If you want to squeeze G and use something that's only slightly rectangular, then the entries in G inverse of X will be bigger. You remove the redundancy by multiplying it by G on the left. So G times G inverse of anything is anything. And sometimes you actually use it in the opposite direction. You use G to get redundancy by multiplying it on the right. So, G is this wide and short matrix. If you multiply it on the right, you get a bigger dimension and therefore more redundant. And you can use that sometimes. With that, I want to show you the other crypto system that will come into play in my talk, and this is the GSW type crypto system. These are used to encrypt scalars. Typically, it's a lot harder to use them to encrypt matrices, and I'm going to talk about it through quite a few slides in my talk, how to do that. But the thing that I want to draw attention to is the decryption invariant. As opposed to Regev, where you have S times the ciphertext equals something about the plaintext, here the secret key appears on both sides of the equation. So S times C is your plaintext times a redundant version of the secret key plus a little bit of noise. That difference, so I put both decryption invariants here on the slide so that you can compare them side to side. That difference in having S also on the other side of the equation makes a big difference in how you work with this crypto system. And a lot of the magical property of GSW come from that thing. To encrypt this scalar sigma relative to a secret key that looks the same thing as S concatenate with the identity, you generate the same pseudo-random matrix as before, but now instead of now you add to it sigma time this G matrix, and you can check that the decryption invariant is satisfied. But doing that rely on the fact that multiplying scalars, you can multiply the scalar on the left or on the right of the matrix and it commutes. So just in terms of properties, Regev is for matrices, GSW is for scalars. The invariants are different. They're both additively homomorphic in an obvious way as long as the noise doesn't grow too much. And they both turn out to be multiplicative homomorphic. For Regev, it's a complicated way to do it. I'm not going to talk about it. The only thing that's important about it is that the noise, when you do this multiplication operation, the noise is symmetric in the noise of the two matrices that you two ciphertexts that you multiply, essentially a sum of them times some polynomial factor. For GSW, the multiplication is simpler. You take one ciphertext, you multiply it by this redundant version of the other, and the noise is not symmetric. The noise in the first ciphertext still get multiplied by this polynomial factor, but the noise in the second ciphertext just get multiplied by whatever plaintext was inside of C1. So if you think about it, if this plaintext was a 1, then you just get this noise. And if this plaintext was a 0, then you don't get this thing at all. So it's a very asymmetric way for the noise to grow as you multiply. And I think this is, yeah. And with that, I covered all the background that I need. So I'm going to spend the next part of the talk talking about how to use GSW to encrypt matrices rather than scalars, and an application for homomorphic virus scanning. So the question of how to use GSW-like thing to look at to encrypt matrices was looked at a couple of years ago by Hiroshima, Abe, and Okamoto. So again, the invariant, the decryption invariant is basically the only thing that's important about homomorphic cryptosystems. This is the GSW one. And we want to use the same invariant in order to get the same properties to encrypt matrices. So we want to encrypt a matrix in such a way that S times the ciphertext equals the message time the secret time this redundant version of the secret key plus a little bit of noise. And we can't really, because the reduction to LWE, or if you want, the way to encrypt, relied on the fact that the sigma and S commute, and if instead of sigma you have a matrix M, then M and S, well, matrix multiplication is not commutative, so it just doesn't work for syntactic reasons. But think about it for a second as a secret key encryption. Well, if you have the secret key and you wanted to encrypt M, you could choose error E and just compute, solve for C, find some C that satisfies this decryption invariant, and that would satisfy the invariant. So this does give you an encryption scheme. It's just not clear if it's secure, or if it is, under what assumption. So here is one thing that that you can always do, or at least in this context you can always do. Well, instead of having one secret key, just have a leveled system where you have many secret keys and change your decryption invariant so that Si times C is M times Si plus 1 times G plus E. It's the same idea that was used in this graph-based multilinear maps of Gorbunov et al. Where you have, you think about it as a chain of secret keys, and every ciphertext moves you from one secret key to the other. In the multilinear, multilinear map case, there is an issue that you need to publish one of them, and that gets you into a lot of trouble with security. But really, we don't publish any of them, and you can prove security based on LWE. That's very easy. Basically, you can the ciphertext looks pseudorandom even if you know Si plus 1, as long as Si is secret. It does degrade functionality in the sense that you can only multiply ciphertext in order. So you can only multiply the C1 by C2 and C2 by C3, but not C1 by C3. And if you do multiply them in order, then the product encrypts the product of the plain texts with respect to this hop that jumps through the next secret key. And you get LWE security for secret key of this same form that we had from before, SI, with the identity. The proof is straightforward. I mean, there's nothing to it. You just show that you have the same pseudorandom matrix there. So that's good. So at least in some cases, if you can withstand the loss of functionality, then you can recover security. And if you don't want to, then, well, just replace all these S's by the same S, call it circular security assumption, and that's, well, we use circular security assumption a lot in homomorphic encryption for various reasons, but it's just a euphemism for we don't know how to do anything with it, and we don't know how to break it either. So I'm going to stick with this leveled notions just so that I don't have to worry about security issues. But I want to talk about efficiency considerations. And there are two reasons why this matrix GSW is inefficient. So you start with a plain text matrix, which is an n by n matrix. And then first off, the ciphertext has more rows than the plain text. And second, the ciphertext have even more columns than rows. So these are two sources of inefficiency. The ciphertext has higher dimension than the plain text. The second of these things, the fact that the ciphertext has more columns than rows, has to do with the shape of this gadget matrix G. Remember, it has to be rectangular, and the more rectangular we can make it, the smaller the entries of G inverse, and then when you multiply matrices, when you use GSW to multiply matrices, the noise grows slowly. You can reduce this overhead by squeezing G, making it less rectangular, then the difference in dimensions will get smaller, but the noise will grow faster. I'll get to it in the next bullet. Thanks. So let me finish this thing. This, when you try to actually build an application, there is a trade-off that people sort of understand pretty well. In many applications, eventually what you discover that the best setting is that the G matrix is sort of has maybe 3 or 4 times as many columns as rows, which means that the same thing holds for your ciphertext. So this is one reason why that thing is inefficient, why the ciphertext is bigger than the plain text. And the second one, for Alon's question, was the fact that your secret key has this shape of secret key concatenated with the identity, which means that it has security parameter more columns than rows. And sometimes it's important and sometimes it's not. There are applications where you can set n to be much bigger than the security parameter, and then this overhead doesn't matter much. But n is something that comes from the application. The plain text is an n by n, and maybe your application only needs a small n, in which case this will be an important factor. So sometimes it does matter. And the next thing that I want to talk about is, can we at least get rid of that factor? I mean, the other one, we sort of understand where the trade-off, and we're stuck with it. What happens with this? Can we get rid of this additional thing? What we want is square secret keys. And, you know, square mod Q, let's just assume that they're invertible. They will be if you choose them at random with high probability. Let's suppose that the secret key was square and invertible, then the ciphertext, you can actually write it as S inverse times M times S prime times G plus E. Okay, so there's a sort of a closed form formula to compute the ciphertext. Again, think about it as secret key encryption that gives you an encryption scheme. And again, the question is it secure? Is it secure? Here, even though we're using a different S and S prime on the two sides of the equation, we cannot reduce it to LWE. So the question, can we reduce it to anything? And in this work with Nick and others, we introduced a new assumption related to the entry assumption. We call it the matrix inhomogeneous entry assumption. And we show that this crypto system is secure under that assumption and a few other things about that assumption. We study it a little bit to see if it makes sense. So let me describe to you what this thing is, explain why it's related to N-true, and say a few words about it. So I'm going to describe to you the small secret version of the min-true assumption because it's a little easier to describe and it's a little closer to N-true. So you choose your secret key. Now it's a square matrix with small entries. You also choose many square error matrices, E1, E2, up to En. And the thing that you output is the identity minus E1 divided by S, twice the identity minus E2 divided by S, 4 times the identity minus E3 divided by S. If you want to think about it, you can concatenate all the E's, and then you do G minus this matrix of all the E's multiplied by S inverse. So I want to point out the similarity to N-true. In N-true, the N-true crypto system with the N-true assumption that underlies it, you have a public key that consists of a ratio of two small elements in rings. So think of G1 and F as matrices for now, even though they're special matrices that represent ring elements. So you have G over F, and you assume it's pseudorandom. You can extend that assumption to have many of them with the same F. So you have G1 over F, G2 over F, Gn over F. And in our assumption, we're using an inhomogeneous version of it, where in the numerator, you also have some constants, the identity, twice the identity, 4 times the identity, etc. And we're still assuming, we would like to assume that the output is pseudorandom, and we don't need the ring structure. So, I mean, it's similar to N-true, but in our case, we don't actually need the ring structure. So, yeah, I mean, I didn't show you the non-homogeneous, the non-small secret thing. The non-small secret thing clearly implies N-true, well, except for the ring thing. I mean, if you did that over a ring and you used the other one, then it clearly implies N-true. It also implies this, this small secret. And this assumption also implies security of the crypto system. There is no proof in this. I mean, you just write down the assumption and write down the crypto system, and you get the exact same thing, with the exception that the way you choose the error, if you start from the assumption and describe the crypto system this way, the way you choose the error turns out to be weird. This is the way the crypto system chooses the error, just so that we can actually show this reduction. But it means that in the crypto system, the way you choose the error depends on both the secret key and the plaintext. So it has to be a secret key encryption scheme. You need to know the secret key and the plaintext in order to choose the error term. So you get a symmetric encryption scheme. But this is homomorphic encryption. Symmetric and asymmetrics are equivalent anyway. There are generic ways of transforming one to the other. So that's not a problem. And in some applications, you don't care about it because you don't need public key encryption. So this is one answer to the question of whether you can get a square secret keys. Yes, you can if you're willing to assume that. And we talked a little bit about how reasonable or not reasonable the assumption. We also have some Oracle version of LWE that would imply the hardness of this assumption. I don't think that the Oracle version of LWE is any more believable than that assumption, so I didn't put it here. But there are a few things that we can say about this assumption. The small secret and non-small secret are also equivalent, and things like that. And some cryptanalysis of why we do or do not believe that this assumption is hard. So with that, let me just describe to you one application of why you want to have GSW-based matrix encryption, and this is the application to virus scanning. So traditional virus scanning, you have a data center or a company that runs an antivirus, that has an antivirus product, and you have all the clients that actually run the antivirus. And the center just keep pushing virus definitions onto the clients, and then the clients check these virus definition against their local files. So the client has the virus definition, they have the local files, and they check for a match. And what these virus definitions are really just regular expression. I mean, if it matches these 5 regular expressions, then you have the virus, essentially. And also a very simple regular expression at that. I mean, a few things should be a particular characters, everything else could be anything at all. So this is how virus definition typically work, and the question that started us thinking about it is what happens when the virus definition itself could be sensitive. So for example, it's an exploit that we discovered at our company, but is not known in the wild yet. We don't want to advertise it to everybody by pushing these simple virus definitions. So can we hide it some way and still be able to test, to let everybody test? And the architecture we had in mind is this. Instead of sending the virus definitions, I'm going to send an encrypted version of the virus definition. The client will take their plain text files, match them against the encrypted definition, get an encryption of the result, this no match result, will send that encrypted result back to the center. The sender will decrypt, and then the center will know whether you have a virus or not. And if you do have a virus, well, then there's something you need to do. But at least the part of discovering, you don't have to expose your virus definitions for that. Now, well, these are regular expressions, so you can represent them by a nondeterministic finite automata. And the way you evaluate a nondeterministic finite automata on a string is you just choose whichever matrix transition matrix you want based on the bits of the string, and you multiply them. So the files are in the clear, just the matrices that are encrypted. So all you need to do is matrix multiplication of the encrypted matrices. So you really want to encrypt matrices by a homomorphic encryption scheme that lets you quickly evaluate matrix multiplication. And here it turns out that the non-symmetric nature of GSW noise growth is crucial for that application, and the reason is this. How do you, right, I mean, this is the thing on the top is how you evaluate a non-deterministic finite automata. There is a vector V corresponding to the initial state, and you just multiply it by a whole lot of matrices. How do you do that? Well, there are 2 ways to do this. One is a balanced multiplication tree, which is nice in the sense that the depth is low, but is nasty in the sense that you need to do matrix by matrix multiplication. The other one is you do it sequentially. First multiply it by M1, get another vector, then multiply that other vector by M2, etc. Now you only do matrix by vector multiplications, so you save a factor of n in work, but it's sequential. The depth here is n. If you were to use Regev type crystal system to do that, the big depth will kill you. GSW, not at all. You can do this non-symmetric noise growth and make sure that the thing you multiplied is always the one that, you just get added noise for every level of multiplication. So you really want a matrix version of GSW. This was our motivations for looking at that problem to begin with. And it turns out that using that property and, excuse me, using this optimization, right, and n here could be small because the number of states in this non-deterministic finite automata could be small. So there really is a reason why you may want to remove this additional security parameter, many rows, many columns. Just, a few words about the last step that I didn't describe yet. You want to convert the virus definition to non-deterministic finite automata. Right, I mean, there are many ways to convert a regular expression into NFA. So first of all, we want NFA with small number of states. But also turns out that we want the ambiguity of the NFA to be limited. The ambiguity of the NFA is how many accepted paths you have at the most. And because GSW's noise is, there is a term that gets multiplied with the plaintext, and the plaintext is bounded by the largest entry in this matrix, and the largest entry in this multiplication matrix is how many paths you have, then you really want to be very few paths. Now, NFAs with small ambiguity exist. In fact, in some cases, you can have NFAs with ambiguity 1. So you have at most one accepting path and still be much smaller than a deterministic finite automata. So there are ways to get the ambiguity to be small. There is an optimization problem that you need to try to solve, and this is, given a regular expression and some bound on a number of states, find me a non-deterministic finite automata that minimize the ambiguity. That thing is, as you can expect, an NP hard problem, but there are useful heuristics to solve it, like taking partial derivatives of NFA with respect to the different alphabet outputs, and they work well in practice. So when you take all of these and put them together, you get a system that's almost workable for some parameters. So you can evaluate NFA with maybe 1,000 states on inputs of meaningful size, like from 256 up to maybe a few tens of thousands of bits in minutes or seconds. These are the implementation. They're not particularly well optimized, but I want to draw your attention to the fact that ciphertexts are still big, even with all of these optimizations. Because Q, the modulus was still big. Well, not huge, but big. I think it can be made much smaller, but we only pushed it a little bit. So the matrices themselves that we encrypt are 0-1 matrices because they are transition matrices of NFAs. The ambiguity, this was done on regular expressions that gave rise to very small ambiguity. So the numbers, even in the product matrices, didn't grow beyond. I don't remember what the number was, but it was a small number, maybe 100, maybe less. And again, I don't think it will. What?
So the plaintext is about 1 million bits, like
1,000 by, yeah, about 1 million bits, or maybe 10 million, or something like that, yeah.
What's the size of the variance?
So the thing is, the regular expressions themselves are extremely simple. So you can get by with a lot less of 1,000 states, which means that you can stuff one of these 1,000 by 1,000 matrix with maybe 20 or 50 of these regular expressions. So if all the secret definitions that you want are only 20 or 50 regular expressions, then one of those will be enough. And then you would run it, I guess, on chunks on your bits. So you're stretching the imagination a little bit, but even these performance, you could maybe even use them. And I'm guessing like 1 or 2 order of magnitude if you really try hard to optimize, you can get. So I think we never actually got to a point where we try to convince people to use it, but I think if we had, there was a chance that it would be workable. How much?
How old is it was, which is like the previous FEG and as a new
So, you know, if it's this, I think it will be at least a number of hours, maybe more, just because, you know, HElib is a regev type encryption, so you have to go through the balanced thing, which means that it's 1,000 thing just with the amount of work. That would probably be even slower, right? I mean, 1,000 by 1,000. The thing is, you don't have to have 1,000 by 1,000 matrix. I mean, you can, if the NFAs are, if the regular expression is small enough, you can just send them one at a time. So I didn't go through the things. I'm assuming it's still hours, but I never actually went through the exercise. How much time do I have? Okay, so I'll give you just a glimpse of the other work, and many of you already heard about it anyways. So the other one is compression and efficient private information retrieval, and the starting point of this is, well, okay, so we optimized a little bit the GSW encryption of a matrix, but we didn't get too far. I mean, there's still a big gap between the amount of information that you process and the size of your ciphertext, and the question is, can you do better? And with GSW, the answer is sort of no. Just because your G matrices have to be reasonably wide and short. So can we do better with regev type encryption? So let's look at just the way we did the GSW. Let's look at the inefficiency of a regev encryption. So here's the invariant. Secret key times ciphertext equal an encoding of M plus noise. And there are 2 reasons why the ciphertext is bigger than the plain text. One is, again, the shape of the secret key, which is S prime concatenated with the identity. And this time I'm not going to look at this aspect because, again, there are some applications where you can take N to be large enough, and then that factor doesn't count for a whole lot. And the other one is you need to encode the message in order to recover it after the noise. So, you know, if you are able to make the noise small enough, then this one doesn't count for a whole lot either, because, you know, if the size of the entries are sort of epsilon times Q, so the size of the entries in the noise is epsilon times log Q, then this is just another factor of epsilon. I mean, the encoding of M should be bigger than M by some factor of epsilon, and then at least information theoretically you can recover it, and with the techniques that we have, it's also very efficient. Usually this encoding, by the way, is just multiplied by a large enough factor, so a constant factor. So you can just get rid of the low order bits and you'll be fine. And again, this is epsilon. So if you want, in principle, regev encryption can give you 1 minus epsilon rate for any epsilon that you want, if you can keep the noise small enough and you're in an application where N can be big enough relative to the security parameter. So that's basically what it is. You just need to keep the noise small. And keeping the noise small is the thing that in the entire field of homomorphic encryption is about keeping the noise small. So we have lots of techniques. Unfortunately, they typically work better for GSW than they do for regev type encryption. And here we want them to regev type encryption, which brings up the questions of, can we get the best of both worlds in some sense? So we want to get the slower noise growth of GSW with the high rate of regev. And can we get that? And in some cases, you can use using this notion of compressible homomorphic encryption. What it is, you just use GSW to do your calculation, and at the end, you take all of your GSW ciphertext and you compress them into a regev ciphertext without much bigger noise. and then the size of the ciphertext gets smaller. It does not help you to compute faster, typically, if you have a complicated computation, because you do the entire computation with GSW, but it does help on bandwidth, and in some cases it also helps on computation. I'll maybe mention it in a slide if I have time. I'm just going to go through a useful observation that allows you to take GSW ciphertext, encrypting bits and compressing them into a Regev matrix, a Regev encryption of a single matrix. So the observation is if you have a GSW encryption of some scalar, a small scalar, and you have a Regev encryption of a matrix, then you can just apply the GSW multiplication operation to them, and it gives you a Regev encryption of the product between the scalar and the matrix. And that's nice. It lets you move from GSW to Regev encryption in some sense, if you have it. Here's the proof. It's just algebra. You have these two invariants at the top, and you have your C1 times G inverse of C2 ciphertext, and you multiply it by the secret key. So you get the GSW invariant first. You open the parentheses. You get G times G inverse that goes away. And the only interesting thing that happens here, other than opening parentheses, is you have a plain text time encoding equals an encoding of, you bring the plain text inside. Well, if the encoding is linear, which it is always in Regev, we always use an encoding linear, then you can always do that. And other than that, it's just algebra. And the size of the noise, this is the regular GSW term for noise. So you can multiply GSW ciphertext not just by one another, but also by Regev encryption, and it still works, which is nice. There's even a better version of it where you have the plain text instead of the Regev encryption. If you have a plain text, then you encode it in this particular way, and then you can also multiply it by GSW ciphertext. The reason being that that green thing up there is a noiseless Regev encryption because it satisfies the invariant. So that's nice. And now you can use it to compress. So suppose you have many encryption of bits, GSW encryption of bits. You want to pack them in a Regev encryption of a single matrix such that sigma ijk is the kth bit of the ijth entry of M. So M is that thing at the bottom. Then, well, what you do is you just look at all these matrices, singleton matrices that have only the kth bits of the ijth entries 1 and everything else 0. Use the observations from before. You multiply each one of them by the encryption of the sigma ijk's that we have. You get an encryption of that matrix. And then Regev encryption is additively homomorphic, so you add them all up. And that's it. So it's really very easy to take many GSW encryptions and just pack them all together in a single matrix. And now I have like 3 minutes. I'll talk about, will I talk about it? 3 minutes, really? Okay, I will talk about it a little bit because I think it's nice, and also it's really, really simple given everything that we did so far. So we want to do private information retrieval, right? There is a client, there is a server. The server has a big database. The client wants to ask for a single entry, doesn't want to tell the server what that entry is and want to get the answer. And then the communication has to be much smaller than the size of the database, okay? And this is the this is the Kushilevitz-Ostrovsky construction. You look at this database as an entries database. You look at it as a matrix of N1 by everything except N1. And in our context of homomorphic encryption, the client will send an encryption of all these bits. So instead of sending n bits, the client can send only n1 bits. And the server will just multiply these encrypted bits by the database and get an encryption of the rows. So all the other rows are zeroed out. The row where the entry that the client is interested in is the only one left. You can add them up because it's additively homomorphic. You get a new database. Now it's encrypted database with the entry still there. And then you recurse. And again, in our case, you would use the multiplication by plain text on the first thing, and in the other phases, you're going to have to use the multiplication by ciphertext. But the observation that I described to you works equally well in both cases. So you just send GSW encryption of all these bits, and you keep doing that, and every time you get a compressed regev encryption of the database. And really, it's only the first step where you do any work, because this is the first step where you touch the entire database. And after the first step, the database is smaller by a factor of n1. So what you do after that doesn't count all that much in amortized sense. So that's it. This is where the magic happens. You multiply it. This yields a regev encryption of the database that's compressed. And the same holds for the recursive links. And then you can actually, it turns out that you can actually make that one into something that's presumably is fast. I never implemented that. But just when you do the calculations of how much work you're doing, the amount of work that you do for every byte in the database is something like 2 or a little under 2 modular multiplications for small primes, like 60-bit primes or something like that. So if you compare it, it's faster than what it takes you to compute AES in software. So it's a public key construct, like private information retrieval, and it runs faster than this symmetric key AES, which is a relatively rare thing. And the reason it works is because you can compress it, and you can compress it very, very quickly at the very beginning. And after that, you do some more operations that don't matter all that much because you're doing it on a lot less data. Okay, so that's all I wanted to say. I talked about techniques for reducing the gap between the size of the ciphertext and the size of the plain text. Roughly speaking, it boils down to encoding things in matrices and converting between GSW and regev when you need to. Some of these conversions are easy. The observation that I showed you, you just need to multiply it by the matrix. The other direction seems to require bootstrapping, so it seems to be harder. And in certain applications, you actually get very fast solutions.